Thank you for coming to my talk, Modeling Change Points and Performance Variability in Large-Scale Naturalistic Data, by myself, Michael Collins, and my co-authors Florian Sense, Michael Kruzmark, and Tiffany Jazer-Zembensky. The study of human memory has been a primary interest in psychology due to the fact that it has implications for both education, medical, and military applications. Though empirical research has found many different regularities in memory, I will focus on three robust features of memory here. The first is the power law of learning. As experience increases, performance improves. Second is the power law of forgetting. As time between instances of practice increases, performance decreases. And third is the spacing effect. When instances of practice are spaced further apart, acquisition is slower, but retention is greater when compared to a mass learning schedule. These features of memory are often combined into models of memory and learning and retention, which attempt to explain and predict performance of individuals over time based on their learning history. The model that I'll be talking about today is the predictive performance equation, also known as the PPE, which I will now give a brief overview of. The PPE is composed of 7 different equations shown here. The model has 4 fixed parameters: lag, time since the previous presentation; t, the time of exposure; n, the number of exposures to some item; and c, a learning rate, which is traditionally held constant. PPE has 6 free parameters: b and m in equation 4, representing the decay intercept and slope; tau and s in equation 6, representing the performance intercept and slope; and uppercase and lowercase a in equation 7, representing the minimum and maximum performance value. With these free and fixed parameters, we can compute the different terms within the PPE: T, model time; ST, stability term; M, activation, probability, and performance. Though the PPE has successfully accounted for human performance across a variety of different domains, it, along with other models of learning and retention, assume that performance will follow a smooth performance curve, which comes with 2 assumptions. One, these models assume that performance is generated from the same mechanism, and 2, that individuals have stable subsymbolic parameters such as learning and decay rates. The assumption of a smooth performance curve comes from looking at empirical data of average performance over time. As an example, on this slide, we have performance of individuals completing Luminosity game from Kumar 2020, shown here in red. As seen here, average performance shows a smooth performance curve with individuals slowly improving over time. However, if we plot the individual participant performance as a function of time, shown here in blue, a different feature arises. We see that 1, there's a great deal of variability across participants in their performance, and 2, individual performance profiles do not follow a smooth performance curve. This difference between average and individual learning curve suggests, as others have pointed out, that their smooth performance curve is an artifact and that individual performance does not often follow this smooth trajectory. Though the performance of individuals might not follow a smooth continuous performance curve, this does not mean that deviation from continuous performance is simply noise or error on the side of the individual. Other researchers have shown that over time, discrete performance shifts can be understood as individuals changing their strategy, mechanisms, or heuristics in the domain of skill acquisition, decision-making, and learning. These insights have been found by taking standard psychological models and integrating them with change detection algorithms, which allow for the estimation of different discrete segments within longitudinal data, which are accounted for by different models or different sets of parameters. A majority of research examining changes in performance over time in learning have been conducted in laboratory studies where the task is amenable to different strategies, psychological mechanisms, and heuristics. Little research has examined the characteristics of learning in a naturalistic setting where individuals differ in the degree of motivation and study strategies and can freely choose when to study. To better explore the variability of learning profiles in a naturalistic dataset, we conducted a model comparison study on a naturalistic dataset collected by Kumar et al. 2022 of individuals completing games on Luminosity over a period of several years. For the model comparison, we have implemented 2 different versions of the PPE: a continuous PPE, which was the normal version previously discussed, and the change PPE, which takes the standard predictive performance equation and integrates that with a change detection algorithm. In addition to the model comparison, we made 4 hypotheses about the expected performance of individuals in this dataset. First, we predicted a majority of participants will have at least one change point inferred from their performance. Second, we predicted that there will be a positive relationship between the number of change points inferred in an individual's performance and the number of performance opportunities. Third, we predicted a majority of the change points will occur after a brief lag. And fourth, we predicted a positive correlation between the number of inferred change points and the individual's improvement over time. For this study, we used a randomly sampled subset of 1,200 participants of data organized by Kumar et al. 2022. We examined the participants' performance on the loss mitigation. We examined the participants' performance on the loss migration task on luminosity inspired by the Ericsson flanker task. During each trial, individuals were shown birds moving across the screen and had to report the direction the birds were flying while ignoring distracting signals. The data was already formatted into trials, sessions of continuous gameplay, and performance was measured by the number of correct gameplays per trial. Two different versions of the PP were both fit to each participant's performance. The continuous PP estimated 6 free parameters for the participant's entire performance history, while the change PP used a standard PP as well as a change detection algorithm to fit to the participant's performance using a genetic algorithm. Each model was fit by attempting to minimize BIC. BIC was chosen as a measure of fit due to the fact that BIC takes into account the likelihood of the model fit, number of free parameters, and the number of data points to balance both the model's ability to fit the participant's performance against the model's complexity as measured by the number of free parameters. We'll now review the change detection procedure used to fit the change PP using a genetic algorithm. First, the genetic algorithm proposes a population of multiple sets of potential change points within an individual's learning history. Then, a single set of change points is selected. The individual performance is separated into individual segments, and each segment, the PP is fit to each individual segment using maximum likelihood. From these fit and the number of free parameters, the BIC is calculated. This process continues until each individual set of possible change points has been evaluated. The genetic algorithm then checks for convergence, looking at the number of iterations and the times it has found the lowest current BIC value. If convergence has not been reached, then a new population based on previous results is propagated and the process starts over again. If convergence has been reached, then the set of change points with the lowest BIC are selected. We will now look at the results of our model comparison, comparing the two models' ability to fit the data, as well as evaluating our 4 hypotheses for this paper. First, we compared the participants' average performance as a function of instances of practice of the participants, shown here in black, and each model's fit to the human data. Change PP is shown in red, and the continuous PP is shown in blue. From the figure, we can see that both models fit the average performance fairly well, while the change PP has a slightly higher correlation and lower RMSD compared to the continuous PP. However, if we look at performance at the individual level instead of the average, a greater difference between the two models can be seen. Here we see the performance of a single participant where the change PP estimated 4 change points. The change PP's fit is on the left and the continuous PP's fit is on the right. From this participant, we can see that the change PP is able to better fit the participant's performance over time and estimates a greater amount of certainty, as noted by the confidence intervals marked by the multicolored ribbons. However, the continuous PP, here on the left, is seen to have difficulty in accounting for the participant's performance over time, underfitting the participant's later performance, and having a higher degree of uncertainty in estimates, as noted by the larger confidence intervals marked by the red ribbon. Now that we've compared the fit between the two models, I will evaluate the results for each of our 4 hypotheses. For our first hypothesis, we predicted that a majority of participants will have at least one inferred change point. To evaluate this hypothesis, we examined the number of change points that were inferred across the subset of participants examined in this paper. Across all participants evaluated in this paper, 52% of participants were found to have at least one change point inferred from their performance, confirming our first hypothesis. For our second hypothesis, we predicted that there would be a positive correlation between the number of inferred change points and the number of trials completed by the participant. As predicted, there was a moderate positive correlation of 0.48 between the total number of trials completed by a participant and the number of inferred change points. This finding is in line with our second hypothesis and suggests that as participants gain more experience with the task, they will change how they complete the task, potentially using different strategies, different psychological mechanisms, or different heuristics. For a third hypothesis, we predicted that change points would be more likely to be inferred after brief lags between trials as opposed to longer lags. To assess this hypothesis, we examined the time between when a change point was inferred and the previous trial. From the figure, it is seen that change points do occur after many different time points. However, the majority of the change points occur within a day of the last presentation. This finding suggests the majority of the change points identified by the change PP arise due to a shift in strategy and not simply due to an inability to recall or simply memory decay. For our final hypothesis, we predicted a positive correlation between number of inferred change points and the individual's improvement on the task over time. We examined the average proportion of performance change as a function of the number of inferred change points across participants. As can be seen in this figure, there is a strong positive relationship between the number of change points and the proportion of performance change. This suggests that the inferred change points are associated with greater increase in performance over time and not simply due to noise, error, or lack of motivation by the individuals. I will now review the goals of this talk, our results, and some of their implications. In this talk, I've reviewed a model comparison evaluating two different versions of the PPE. One which assumes a standard continuous performance curve, and the second which incorporates a change detection algorithm allowing to account for sudden changes in performance. Both models were applied to a naturalistic data set collected from Luminosity, and the results from the comparison revealed 4 important findings, each of which supported each of our hypotheses. First, over half the participants there were inferred at least having a minimum of 1 change point. Second, there was a positive relationship between the number of trials completed by the participant and the number of total change points inferred. This suggests that the more experience an individual has, they will refine their strategy or memory representation of the task. Third, we found a majority of change points were inferred soon after a recent trial, suggesting that changes that were inferred are not simply due to memory decay. And finally, we found an overall strong positive relationship between the participants' change in overall performance and the number of inferred change points, which strengthens the claim that the performance changes were made in order to improve their performance on the task and not necessarily due to a lack of attention, mind wandering, or lack of motivation. The implications from these results are twofold. First, we've shown that at the individual level, performance is not always best characterized by a smooth performance curve. Second, individual performance is often marked by sudden and discrete shifts in performance, which might suggest changes in their strategy, heuristic, or mechanisms used to complete the task. Though the results represented here are promising, we have 3 limitations and applications for future research that we would like to address. First, for the results presented here, we had to choose the maximum number of possible change points that could be inferred in an individual's performance. This limitation is fairly common with other change detection approaches. However, in our future research, we would like to explore allowing for a larger number of possible change points better account for the data. Second, in this paper, we only evaluated the ability of the 2 versions of the PPE to fit the participants' performance. However, for the change detection approach to be more applicable in applied research, we would like to incorporate this change detection methodology to allow for out-of-sample performance predictions. Third, and finally, we can make no strong claims about what mechanisms generated the inferred change points. In order to do this, we need to find a data set which allows for both accuracy and response time measures to make some inferences about the mechanism underlying performance. In conclusion, many different models of learning and retention have been developed, with each model accounting for similar aspects of human memory. Though these aspects of memory have been identified through the use of laboratory studies where there is a great deal of control in both the content and history of learning schedule. Other research has shown that as tasks become more complex or the control of the participants is weakened, participants will use a variety of different strategies, mechanisms, and heuristics to solve the task at hand. And the effectiveness of only using standard memory phenomena to account for behavior starts to diminish. Our research here supports the claims and highlights that in a naturalistic environment, individuals show a wide range of learning and performance curves, and that models of learning and retention should be developed to account for these aspects of performance. Thank you for listening to my talk. I look forward to interacting with everyone at the conference. If you have any questions, I would like to point you to our paper or feel free to reach out to me via email. I would also like to say thank you to my co-authors and to Kumar and his colleagues for making the luminosity dataset public, and would encourage anyone who's interested to check out the dataset on their own and the analysis they have conducted with the same dataset.